Thanks for having me here. This is joint work with Vineet and Vijay, and we've had too few constraint programming talks here. It seems like Prakash has done a lot of stuff here. So this is going to be mostly a talk about constraint programming, and it's a very subjective tour of some of the stuff I've done with Prakash, other stuff which Prakash is involved in. And mostly what I'm going to try to do is give you my perspective of the blocks that build up to the little language which is presented in the proceedings. And so here I'm focusing more on the building blocks. Hopefully some of you will find different ways to reconfigure them. Yeah? But before we do that, so first I should tell you a little bit. I went to Cornell in 1987. Dexter was doing one of his chair rotations then, and I joined Prakash, and my first research project with Prakash was in 1988 summer, and somewhere around that time there were the stone duality lectures which Prakash and Dexter organized, and it's an addiction that I have still not gotten out of. So, and there's you've seen Prakash and you've seen Dexter, and these guys are always cheerful, happy. But what you do not know, you all need to be aware of, is they're not always very cheerful, and I can attest to that. So I think this must have been around sometime in the early, in 89, 90. I went into what Cornell calls a exam, which is their Cornell's version of a thesis proposal exam. So this was a Friday afternoon. My exam started at 1, and it ended around 6. And to this date, my housemates swear that I came out looking as if I had a concussion. There you go. I'm still here, so it wasn't that bad. So let's start here. So here is so this id was old language. This was built in the Dataflow group at MIT. So what they were trying to do was, so this was when they were trying to build Dataflow machines. There were lots of small nodes. This is parallelism, I guess, on the small scale, and they were exploring how to program this machine, right? And they were thinking of functional languages, and then they ran into what was then in the functional programming community people call the copy problem, which is more or less that any time one does an update, unless one is super careful, one ends up making a copy of the data structure. And since at that time there were, the sort of the calculations of interest were a lot of numerical stuff, they wanted something which would work better. So one of the solutions they came up with was to think of updatable shared memory, right? But we wanted to be deterministic. So an idea that they explored in the abstract form was some kind of monotone shared memory. But now the monotone shared memory has logic variables in there. So you can think of these as how terms behave in logic programming. And what are the kinds of things you could do? You could say here I have something x is somewhere in the shared memory. I could say, x itself is an array of some size, which was the only data structure they had. I could say the 0th element of x is 2, or the second element of x is itself an array, so it's a nested data structure potentially. And we want all of this to be deterministic, so we don't want any conflicts, right? So you solve write-write conflicts. Basically, the idea was you solve it by unification. Then you want to ensure there are no read-write conflicts, and one solves that by saying, well, all reads are blocking. So if you're trying to read a variable and there's nothing in there, it's uninitialized as of now. One blocks, and so that's the sort of the abstract version of the language. I think in practice they didn't do full unification. What they had was in the real language was they had essentially what boils down to single assignment variables. Okay, so now let's look at this language, and let's look at some programs in this language. Examples Prakash will recognize from slides Keshav used to write. So let's say we have so first you should think of all these programs as running in parallel, okay? And you should think of the for loop itself not as a sequential thing, but as a shorthand for a collection of parallel activities, right? So here what do we have? We have created an array of some even size. We have set off the, we have initialized the, I guess, the first index in the array. And now basically each index in the array doubles its predecessor, right? So if you want to draw a picture, it's going to look like this. Sort of like that, yeah? And all these activities are happening in parallel, right? So basically, the way to understand this program operationally, because the reads are blocking, is basically it becomes a sequential program. You know, you start at the end and kind of bubble your way down, right? But one doesn't want to really think of these interleavings. So Keshav and Prakash had this idea that we sort of think of programs abstractly in some sense as constraints of some kind, right? So what's the idea here? Intuitively, you want to say, one of the statements is constraining the size of x, and the for loop up there is constraining the even indices of the array, and that's constraining the odd indices of the array. And intuitively, we put them all together. It's clear that we only end up with the array we want. And at this point, I think Keshav had this idea that what we really need to do is to think of constraints as closure operators. Right? So what is the idea here? So we think of the store, which is our collection of variables. We order these by the information order. So any slot which is uninitialized is in the information order less than a slot with information in it. And we put it all together in the natural way. Of course, these slots could be inconsistent, so that's your top element, which is false. And now what do programs do? What programs do basically is they become closure operators on such a store. So for example, you think of the first thing there, which says x is an array of even size. It adds some information about x. Doing it twice does not change anything. And well, if we think of composition of closure operators, what we know is we can think of it, let me think of it concretely for a moment. We can think of it as some complex, any complex interleaving of the two closure operators. And that's sort of, when Prakash showed this to me, I guess this must have been summer of '88, this was very appealing, because this is sort of, it matched one's operational intuition about what is going on in this example, which is, basically we have a closure operator corresponding to one of the for loops, we have a closure operator corresponding to the other one, and magically enough, this composition sort of just puts everything together neatly. But what is perhaps nicer, is that we don't need to think of the interleavings at all. We can think of the closure operator just in terms of its fixed points, right? So here the fixed points are where the array, where x is already an array of this even size. The fixed point of that, the for loop above, is something which already sets the even indices appropriately. The fixed points of that are something which sets the odd indices appropriately. Right? And parallel composition then has this really nice and pretty description as plain old set intersection. Right? So this was the framework which Prakash and Keshav had developed for what at this point was the first order functional language, parallel execution with a shared monotone store in the form of logic variables. So this is where it is. Right. And just as an aside, which is is that already in this simple language, it forces one to think of computation a little bit more symmetrically, right? So let's say we write a little expression in this language, which takes which is a little function maybe, which takes an array and creates an array. So if we are thinking of it in the usual way, we want to think of it like that. We want to think of it as we take an input and get an output. But just the way the mechanics work out here, it turns out that a better way to think about it is much more symmetrically. So really, that diagram is slightly inaccurate. What we really want to do is, we want to think of it as more like that, right? So in particular, the way we want to interpret the expressions is, we want to think of saying, hey, I take my input, and I take my approximation to my output, and I produce a, I may change my input because that's just the way the language is, and I produce a better approximation to the output. Okay. And this idea of, so formally, an expression becomes a closure operator not just on the store and something about the output. There's total symmetry between the way the inputs and outputs are treated in expressions. And this idea turns out to be quite general in the sense that even if one, in later work which I did with Keshav, we looked at this language, but with a real high order proper functional language with logic variables, that view still works. Okay, so, but as an aside, this is a thing I learned from here, perhaps something which has lasted me for many, many years after. Right? So that's, this was all very early 90s. So what has happened since then, right? Partly work which Prakash has done and which many others in the audience have done from other motivations is one does proper concurrent constraint programming now, which means we have a proper notion of what a constraint store is. So it's not just logic variables. One weakens the monotonicity requirements. So there is the natural thing one thinks of, I think, where one uses time to fake updates. So, if I want to change a variable, instead of changing it at this time, I say, oh, it changes at the next time instead. So that's one way one gets it. Or the other way, in a sort of a different way which works here, which is about defaults. I'll show you a little bit of it. And then there's the issue of adding time. So I just want to give you a high-level tour of what's going on here. So the first thing is, so there's the shared store, so now we call it the constraint system. So it's some piece of logic with conjunction, with existentials. You can think of some kind of shared database. There are lots of nice examples for this. There is the terms as they behave in logic programming, which Vijay likes to call her brand. Then there are rational trees. Which is basically graphs, so you can think of it as the structures perhaps that happen when you do unification without a curse check. Or there is the later systems pioneered and investigated by Dexter for doing program analysis, set constraints. So there's a whole range of these examples, and Prakash and Phil and Vijay. They sort of give us an axiomatization of what are the properties of these things. So we don't need to worry about specific, concrete data structures like logic variables. We have some abstract way of thinking about it. So what's the first thing that one gains from looking at it like this? Is that one gets a better language, I think, and I'll tell you why this is a nicer thing. So instead of being concrete, now we have this shared store. Now we say, okay, what can I do to this store? I can add new facts to the store, which in this literature is called tell. I can query the store for a fact, and that has to be blocking, meaning if the store it's not strong enough to give me this fact right now, I'm going to wait there and block. So it's a blocking read, right? And of course I have stuff happening concurrent components working on the store, right? And so that's your basic framework of concurrent constraint program. That's the operational view of constraint program. But I think and the picture we had of closure operators, works nicely here. This was developed in the paper Prakash wrote with Vijay and Martin Renard. So, what are the stores which are strong enough to have A? They are the stores which contain A, and the natural things one writes for this. If the store is not strong enough to contain A, I don't need to worry about the agent. If the store is strong enough to actually contain A, then I do need to run the program. So, okay? And parallel composition becomes set intersection. Yeah? So at this point, it looks just like a replay. But what one gains by looking at it is that one gets a more, I think, a nicer view of what the operational semantics of concurrent constraint program really is. What it is so this is explored by Patrick Lincoln and Vijay. It's a proof search, but on the left-hand side of a sequence. So let's say you're thinking intuitionist logic, okay? So I have this program, so this is my store. I have ask, see, and so this is my implication. I'm reading it as an implication. So let me look at the left rule, right? So what does the left rule do? The left rule says, well, I've got to deduce C, okay? And then I've got to be able to run the right, run the 8. So this is the really nice thing which happens with constraint programming, which is it's proof search, but on the left-hand side. And that's why I'm sort of insisting on the left-hand side, because let's take a little aside. Let's look at proof search as perhaps is more traditional in logic programming. We do proof search on the right-hand side. And a really nice way to sort of a framework to look at this is the framework of uniform proofs of Dale, Miller, Gopalan, the Lambda prologue group. So what is a uniform proof? You're doing an intuitionist proof, so we are deriving G from gamma. Now we're going to look at a very specific form of the proof, where if the formula on the right, is not an atom, then we have to, the first thing we have to do is resolve that top level connected. So for example, if the formula is on the right, it's not an atom, it's B and C, then I expect my proof to do the right interaction rule. Right? And for what is the basic result here? The basic result here is that for a certain class of formulas, namely the hereditary pair of formulas, uniform proofs are rich enough to give you all the proofs. Right? So if one goes and looks at Horn clauses, right? So here I'm going to call these G's and D's. D's are you think of as declarations, and gamma is a collection of declarations. G is a goal, right? So if we look at deduction, the way logic programs evolve, it happens by uniform proofs, but on the right-hand side. Right? So and of course, that does not just have to be. Horn clauses, you can have full hereditary pair of formulas. So you have richer stuff. In particular, your goals can be conditional goals, right? So you really want to prove that, but you can assume something extra. So you get a much more of you're using much more of intuitionist logic, right? So there's all this stuff, traditional logic programming, whether in the prologue form or in the lambda prologue form, which is happening on the right. Then there's all this stuff, constraint programming, which is happening on the left. Okay? So, of course, you can put them together, right? And this is a slide I stole from Vijay, which gives you a sense of how various logic/constraint programming languages kind of fit. So here is the language of constraint programming, okay? And so which is on the left, okay? And then here is lambda prologue, right? And you can actually stick both of them together, and they are not incompatible, and they fit together neatly because the polarities work right. So there is some sense in which polarities, as we understand them, in the other style of logic. Logics and types somehow plays a role, and you can put them all together, so you can actually build a little logic programming frameworks where you explore proofs both on the left and on the right, and it becomes an interesting programming language with some interesting features. Okay, so that's so that's one development which I wanted to present that way. And the second thing I want to talk about very quickly is default logic. Okay? So here again, let me return to an example of Keshav. Right? So what do we have here? So we have an array, and this array, it's 1 to n. It's taking values 1 to n. Okay. What we want to do is we want to find out how many times m is there, right? In the array for each of the i's between 1 and m, and we want to compute this in parallel, right? So of course one writes this program there. It make sense? You just think of this universal quantifier, you just think of it as a shorthand. So basically you say, hey, if my I, I just put I back into BAI, I know it's a long reduction. But now if you look at this formula, if you look at this program, you treat it as a formula, it tells you that B is accurately accumulating all the indices. It does not tell you that those are the only indices. Okay, so as a program, it's, that's all it's telling. So what one really needs to do is to one needs to close the world. And how does one close the world? One closes the world with, something like that, which is sort of writer's form of default. So what does one say? Intuitively, what is one saying? For all this, so we're looking at subsets of the indices which one is accumulating, and this is going to, I will explain in a moment what this is, but this is basically going to ensure that in fact we are able to assert, we are able to deduce that in fact we have only the indices we have put in. Okay? So what is this like? What is this? So let's look at it operationally. So we have our old adding constraints, checking for constraints monotonically in your parallel composition. But we also have this odd thing which I'm going to write as if A, else A. Right? And in order to explain the execution of this language, what do I do? The way I want to think about it is, I'll say, okay, I'll give you a final store. This is going to be the result. And I'm not going to, I'll guarantee for you I won't exceed this final store. Right? That's my B. Now subject to, so of course, so that ensures that when I execute the A, I don't want to exceed B, so I want that. And once I have this final store, I'm able to resolve these defaults. Okay? I'm able to resolve these defaults. I can write a little operational semantics. And of course, this is an awkward language because it has the problems one might think about in terms of default logic. So you have programs without solutions, you have programs with multiple solutions. And whereas default logic says at this point these are bad programs, instead what one can do is one can actually accumulate information about even these so-called bad programs, which is useful compositionally. And so this is this gives you an interesting way to add non-monotonic stuff into constraints. And the only point I want you to take from this slide is, in fact, we don't know how to do a proof search interpretation of this logic. But the external reasoning about these programs is related to writer's default logic. Okay? But now last bit. No, I'll be done. So I have this. Okay, so what do we want to do? We want to do time. Okay, but again, let's do it in a sort of a schematic way. So we have some framework, and we just want to sort of extend it over time. So we have the way to do it, which is the logical framework is the framework of temporal logic. From a programming perspective, what we want to do is we want to think of it as the store being reborn at every instant. And so when we compute at this instant, we work on the store, we calculate a continuation for the rest of time, but the store gets reborn. Okay? So this is just a general way of thinking about it. And programmatically, what we do is we basically add something which you can read as the temporal connective next always. And this is and using this, we can rig up a whole variety of interesting programming constructs from synchronous programming. Like for example, we have an agent, which evolves in time, but we only want it to evolve at the instance where a signal is present. So the timeline kind of looks like that. And in the times when A is not present, it does not evolve, right? And the familiar, you can program interrupts with this. You can program more complicated interrupts with this. So why did we do all of this? We did all of this because what we get, the payoff we get, is we get an analysis of synchronous programming. When I say synchronous programming, I mean in the sense of languages like Ester or Lustre. And we get an analysis of the programming, the reason they're expressive. And also I think we get an independent explanation of the causality issues of synchronous programming. So basically what is called causality here is basically the determinacy issue of the underlying default logic. But now just 2 minutes I can tell you what we did in this. I'm not going to, okay? So what are we doing? We want to do, there's this interesting area which is called complex event processing, right? So here, what is the vision of the world is that there are lots and lots of asynchronous events arising at many different places from different streams. And what we want to do is we want to reason about combinations of these events. So For example, streaming databases are doing things like this. Okay, and now we can do it. We can do it somewhat with the framework as we have so far. But in the framework as we have so far, the programmer is forced to sort of carry with herself a residue of the past explicitly. Okay, so what we want to do is we want to liberate the programmer from having to do this. And as a part of it is we want to maintain the past information in a slicker way. We already know from earlier work how to do it. But another thing which we want to do is we want our programs to move back and forth in time. So I want to write interesting things like this. This is a query you might see in a business logic. If the merchant has been tenured less than 90 days, then they had better have satisfied something. So this query is moving back and then moving forward inside it. Okay? And now we have what I wanted to just say, and this is where I'll stop, is that we have the ingredients to do it. So the ingredients are, these are programs that go forward in time. Those are the programs that query the past. And there is an interesting recursive structure between them, which is mediated by the polarities, exactly like what I had shown earlier. So just so that we can make sure that we don't alter the past. Okay, so that's a good place to stop.